Good morning and welcome to the EasySpin Academy 2020. My name is Stefan Stoll and this is day 3 of our 3-day workshop. Today we will have again 6 topical sessions, and then after that those 6 sessions we'll have a Q&A session which is then followed by a happy hour. So first again, let me remind you that you can post questions on Slido. You can access the Slido and on any other links from our Academy website at easyspin.org/academy. And experts will answer your questions on Slido during the sessions and in the breaks, and also in the Q&A session. And for the Q&A session, I will pick a few questions from the Slido stream and address them for the broader audience. We asked the audience yesterday about preferred topics for the last 3 sessions, which were still undecided as we planned the workshop. Now we do have some topics arranged. So in session 16, we'll talk about how to interface EasySpin with Orca. And we'll also look at a function in EasySpin for magnetometry calculations. This function is called Curry. Session 17, we'll cover a much requested topic, which is talking about broadenings in solid-state EPR and how to model them appropriately. We will also talk about coupled spins. And then finally in session 18, we'll touch upon higher order operators, which are used for high-spin systems or for systems like lanthanides. We'll talk about cardamom, which is a function to simulate EPR spectra based on stochastic and molecular dynamics trajectories. And finally, we'll take a little look behind the scenes of EasySpin and see how it's tested and how it's built, and maybe a brief look into the future of EasySpin. So by now, all the session scripts are complete. If you go to the website at easyspin.org/academy, you can now download a new zip file that contains not just sessions 1 through 15, but all the sessions from 1 through 18, and including the solutions to the exercises. So this is the final zip file that has all the files from the workshop in them. So go there and check it out. Also, the YouTube live stream that we're doing right now, and the live streams from yesterday and the day before, are available for watching on YouTube. And Stefan Pribitzer, who is supporting the technology behind the scenes here, has also subdivided those videos into the different sessions, so you can directly access those individual sessions. At the end of the workshop, we'll send around an exit survey. We'll both send an email, and the link will also be available on the Academy website. Please fill it out so we can learn what worked and what didn't, and when you run this again, we can improve upon things. Talking about email brings me to an important topic. We've had reports that people did not get the emails from academy@easyspin.org. It could have been that those emails ended up in a spam folder. So Stefan has prepared a poll on Slido to ask you whether you got those emails or not. Please answer that poll, and that will help us to track down what the issue is. Finally, let me also still mention the t-shirt campaign that's going on bonfire.com. There are still t-shirts available. Of course, this is a pre-sale. So if you buy a t-shirt now, you can buy it still for another 4 days. Then this will close and the t-shirts will be produced. And they will start shipping at the end of October. So depending on where you are in the world, it might take a while before you get them. But the link is on the website, and go there, get your t-shirt. It's 4 more days. And again, we don't make any profit from this. At the very end, after the last Q&A session, we again have happy hour on gather.town. So come there to track me down or other EasySpin experts and ask questions. Stefan Pribitzer has set up some poker tables in the gather space, which hopefully catalyze a little more interaction between everybody. And you might also want to bring your own beverage to the happy hour. Okay, these were the announcements. Now let's dive into session number 13, which is about looking at some other tools that EasySpin has besides simulation functions and fitting routines. The first thing I would like to point you to are the physical constants. So if you go to the online help, an important section to always look at is the list of all functions by category. If you click on that, it'll show you a list of every single EasySpin function that's available. And one section is about physical constants. So you do have a complete isotope database in there, which you can explore, but you can also use it programmatically. And then there is many of the useful typical physical constants used in EPR are included. First and foremost, of course, the reduced Planck constant, the actual Planck constant, the G value of the free electron, and so forth. Let's see how these things can be used. So for example, let's start out again with clear and CLC. I'm here again in the editor window on the left. I'm just writing a text file. Let's take a frequency, 263 gigahertz, e to the 9. This is in hertz. And 1 E9 is equal to 10 to the 9th for those who are not familiar with this notation. Take a G value of 2. And now let's convert this to a magnetic field using the basic equation of EPR. B equals the Planck constant. This is predefined in EasySpin, times the frequency in hertz, divided by the Bohr magneton, which is also predefined in EasySpin, divided by G. And if you run this by clicking Run Section or pressing Control Enter, we will get the answer here. So the field for 263 gigahertz is 9.4 Tesla. So you can do these conversions manually, but there's a few actually pre-packaged conversion functions. One of them is Megahertz to MilliTesla, MHz to MilliTesla. So there you enter the frequency in megahertz, and if you do the same example, it will be 263,000 megahertz, and the G value equals 2. And so the first is the frequency, and the second one is the G value for which to do the conversion. If you press Control Enter, again, you will get the answer of 9.39 Tesla. The output here is given in MilliTesla. Right? So the canonical field unit in EasySpin is MilliTesla. But if you do your own calculations like up here and you're using all these constants, then you are cleanly and squarely in the SI unit frame without any prefixes. So for example, the Bohr magneton is defined just as joules per Tesla. So if you type Bohr magneton in the command window, it's a little larger here, BMP magn, you get 9 times 2 times 10 to the negative 24 joules per Tesla. Of course, there is also MilliTesla to megahertz for the reverse conversion. There's a small interactive tool that allows you to play around with field, frequency, and G values. It's called EPR Convert. If you run that, it's a very small interface. You can select some frequencies. You can enter a frequency here, let's say 17 gigahertz. You can choose a G value of 2.008. And then you can click on the magnetic field button, the colored button here, and it will automatically calculate you the field you have to be at to get this resonance. And it gives you the field in various units and the frequency or energy in various units as well. And there is some shortcut buttons for X band, Q band, W band, and also for the GE value. For example, a W band with a GE value, the magnetic field is 3354 millitesla. If you have 263 gigahertz and you're looking for a G value of, let's say, 6, then the magnetic field will be 3134 millitesla. And you can change the unit here as well. Okay. Voila. So this is EPR Convert. There's another function that's useful that's called Larmor Frequency. That's useful for folks who are dealing with nuclei and doing ENDOR or ECM. What you can enter here, you can enter your isotope, for example, a proton, and the magnetic field in millitesla. And if you, we can store the results. If you run this, we will see that we get the Larmor frequency of this particular magnetic isotope at the given magnetic field in millitesla. In this case, for the proton, it's 14.9 megahertz. And you can add a few. We could, for example, add the carbon as well, a 14N and a 15N. And here you can see that these Larmor frequencies, of course, spread out. And the carbon and nitrogens are low gamma nuclei with resonance frequencies much lower than the proton. So this is as much about physical constants and conversions that is useful to say in this short session. The next important thing are spin operators. If you if you dive if you scratch a little beyond the surface of EPR, the first thing you will encounter are spin operators. And EasySpin has a full set of functions that support this to build spin operators and deal with them. The simplest one is called SOP, which stands for spin operator. And it calculates spin operator matrices for specific spins. The first input to this function is the spin quantum number. Let's, for example, take just spin 1/2. And the second input is which particular operator you desire. Let's say we want to have the X operator, the SX operator. We can assign this to SX here. Let's sure we clear the command window. And if I run this with Control Enter, I do get a nice matrix that, as you can see here, is 2 by 2 and has the correct matrix representation for SX. We could change this to spin 5/2, for example, and get the SX operator for spin 5/2. And voila, if you run this, you get a 6 by 6 matrix with the first upper and first lower diagonal populated with these non-zero operator matrix elements. You can, with SOP, you can also calculate several operators at the same time. So sometimes it's convenient just to get all operators for a particular spin, and that's done this way. You specify all the operators you want, let's say SX, SY, SZ, give them names, then call SOP, specifying the spin quantum number, and then just a list of the operators you desire, X, Y, and Z. And there is no limit on how many you can specify inside SOP. You just have to make sure you assign as many outputs or pick all those operators up after SOP has calculated them. So let's run this. Maybe we can delete this again. And there you get all three operators, SX, SY, which is purely imaginary, and SZ. So this is how spin operators work for a single spin system. But what about spin operators for multi-spin systems? It's again very simple. Let me take here an example. Let's say we have two spins. I'm going to just abbreviate this now. Spins is 1/2 and 1/2. So these are two spin 1/2s, possibly coupled together. We can get the spin operator for the first spin by saying SOP and then spins and saying X1. This means that SOP will return the SX operator for the first spin. If you want an operator for the second spin, let's say you want to have IZ, assuming the second nucleus is the second spin is a nucleus, that's why we call it I. SOP spins and then Z2. And so if you run this, you can see we get the SX operator with the SX here and the SX here, and IZ is nicely diagonal with alternating signs of 0.5 along the diagonal. You can also get operators that go that are product operators. For example, you get SZIX. You could just now, or SXIZ, let's say SXIZ, you could just multiply SX times IZ now. That is perfectly valid. The alternative is you just ask SOP to return you the combined product operator. First, again, you have to supply the spins, and then you need to say X1 and then Z2. And that will give you, if I run this now, I'm selecting this code and I'm right-click Evaluate Selection. I also can press F9 to run this. Then you get the SZIX operator. Since there are two spins only and there's only two Cartesian coordinates that you're giving here, you can also drop those and just say XZ, and that should give the same result. If you press F9, again, yes, we get the same operator. So this is how spin operators work. In EasySpin, these spin operators are used to build a spin Hamiltonian, which then gives the energy levels. And now let's look at the spin Hamiltonian first, and then at the energy levels. There is a function to construct a spin Hamiltonian. It's called SSHAM. And in order to use it, you have to go back and define a spin system the way it's defined like for any simulation functions. For example, sys.s equals 1/2 and sys.g equals 2. That's a spin system with just one electron spin with a g value of 2.000. We will also need a magnetic field vector, and let's put the field along the z-axis. So we have to write down a vector with an x and the y and a z coordinate, 0, 0, and 350. This is in MilliTesla, and it gives the vector of the magnetic field relative to the molecule. And since everything's isotropic here, so the G value is isotropic, doesn't quite matter in this case. But if your G tensor is anisotropic, then the direction of the magnetic field matters. You will get a different spin Hamiltonian. Now the Hamiltonian symbol is H, and it's called the function for the spin Hamiltonian. It takes two inputs, the spin system and the magnetic field, cis and B. Now if you run this and press Control Enter, we do get the spin Hamiltonian. It is a 2x2 matrix, it's diagonal, and you can see that the two numbers are equal except for the sign. And that just symbolizes or represents the Zman splitting that you have between the alpha and the beta state of a single electron in a magnetic field. The numbers are large because the units of a Hamiltonian in EasySpin are in megahertz. So this is minus 4.9 gigahertz or 4,900 megahertz, and this is plus 4,900 megahertz. And so the difference between these two values is 4.9 plus 4.9, so roughly 9.8 gigahertz, which corresponds to the transition between those two levels. So reminder again, megahertz. Everything is in megahertz that relates to Hamiltonians in EasySpin. We can also build, so as you know, if you have multiple spins, a spin Hamiltonian has many different terms. It has a Zman interaction, it has hyperfine couplings and zero field splittings. And you can construct these individual terms separately with EasySpin functions. So let's add a nucleus to the spin system, proton. Let's add a hyperfine coupling with the principal values 10, 30, and 80 megahertz. And now we can get the Zman interaction for this spin system by just saying Zman of cis comma B. So instead of S-ham, which gives you the full spin Hamiltonian, you just write Zman and you will get only the Zman part of the Hamiltonian. Let's look at it. And here it is. This is the Zman Hamiltonian. It's a 4x4 matrix now because we have two spins 1/2, and each spin 1/2 gives two levels. So 2 times 2 level makes 4 levels. And you can see this Hamiltonian is still diagonal, and it has 4 different energy levels. We can also get the hyperfine Hamiltonian, the hyperfine part of the Hamiltonian, and that is done with the function hfine. Hfine of cis, here we don't have to supply a field because the hyperfine is field independent. If you run this, we'll get the hyperfine term. You can see it looks like this. It has the diagonal is populated and the anti-diagonal is populated. There are other functions for the other terms. For example, there's zero field, Z field for the zero field terms. There's N quad for the nuclear quadrupole, and so on. Now, once we have a Hamiltonian, I hope we still have it here. Yes, we can calculate. Actually, maybe I should take a nitroxide radical. It's probably more instructive. I'm going to take a nitroxide radical. Here's the definition of a nitroxide radical, which I just copy pasted from my prepared session script. G values 2.008, 2.0065, and 2.0023. One nitrogen 14 nucleus, which has spin 1, and an axial hyperfine coupling with the X and Y values equal to 20 and the Z value equal to 100 megahertz. Now I'm going to put the magnetic field, the B field, along the X direction. So 350, 0, 0. We built the Hamiltonian. Let's briefly look at the Hamiltonian. It's a 6x6 matrix. Again, an electron gives two states, and a nitrogen gives 3 states, and 2 times 3 is 6. And we can now calculate the eigenvalues of this Hamiltonian by just saying eig of H. Let's assign this to an energy to E, and let's go look at what those energies look like. You get a vector of numbers, of energies. Again, you get 3 negative numbers, so for the lower electron manifold, and you get 3 positive numbers for the upper electron manifold, right? So you got transitions done between the lower and the upper manifold. To calculate the transitions, all you need to do is subtract E and the transpose of E. That gives you the delta E, the energy difference between individual pairs of these numbers. This is a very useful, Matlab does something cool here called implicit or automatic singleton expansion. That just takes those vectors and then transposes the one and then just kind of constructs the matrix of all the differences between the energy levels. Let's look at it. What we get is a full matrix, and you can see the diagonal is 0 because of course the difference from one of an energy value with itself is 0, and the lower diagonal is positive and the upper triangle is negative. And you can see all the transition frequencies. The EPR frequencies are here 9.8 something. And you can also see in this top quadrant, in the bottom right quadrant here, frequencies in the range of 11 to 22 megahertz. And these are the NMR transitions, which are also possible in this spin system. If you also, now besides the eigenvalues, you also want to get the eigenvectors. You can also use Eig, still the same function, Eig, but you just ask for 2 outputs, V and E. V is the vectors and E is the energies. If you run this now, let's clear the command window up a bit. Then you get a vector for the eigenstates and a matrix for the energies, and a diagonal matrix, right? And so each of these energies corresponds to one of these eigenstates. So for example, the first energy, it's the lowest, corresponds to the first column eigenstate. And this is a representation of the state in terms of the Zman state. So the alpha and the beta for the electron, and the +1, 0, and -1 for the nitrogen. So this allows you to get a little bit of insight on how the spin physics in your system works. Okay. We can take this now to the next level, not just calculate the energies for a single magnetic field, but construct a full energy level diagram. And there's a dedicated EasySpin function for that. Let's start out with just a simple system with one nucleus and a hyperfine coupling of 1.4 gigahertz. This is it corresponds to an atomic hydrogen atom. And let's do now EasySpin's function levels plots this energy level diagram. What you need to feed it is the spin system, then a direction of the magnetic field, let's say the Z direction, some sort of field range, and that's what field range we're going to do here. Let's define a field range from 0 to 600 MilliTesla. Let's give it a field range, and what else do we need? Well, that's it. So now if you run this, here is the plot that pops up, and you can see we've got the lower electron manifold and the upper electron manifold. And if you look at around 0 field, you can see that we get a singlet and a triplet state. You know, an electron and a proton are also a 2-spin system, and at 0 field, only the internal coupling matters because there's no Zman splitting or Zman interaction. And as a consequence, we have a singlet and a triplet state, just like if we had 2 coupled electrons. Okay, we can modify this. Now let's look at the spin 1 system with some 0 field splitting, let's say 5 gigahertz, and make it slightly rhombic. So again, this is in megahertz, and the values indicate D and E of the 0 field splitting. Okay, if you do levels plot of this again, we see we get 3 states, the +1, the 0, and the -1 Zman state, which kind of become obvious at higher fields. But at lower fields, we have a level crossing, and we can see that we have 0 field splitting and some curved dependence. Now you can change the angles. by just changing the direction of the magnetic field. This letter code is a very simple way to abbreviate specific directions, and that's also new in EasySpin 6. So if you want to put the field along the x direction, just type x. And now you can see that the diagram changed, the level crossing is gone, and the quadratic dependence, but the quadratic dependence of the energy level diagrams at the low field is still present. Instead of x and these letters, you can of course enter a phi and a theta angle to specify the directions. And again, these are in radians. And voila, now you can see that the middle level that eventually becomes the mi equals 0 has some interesting dependence here. Now what you can do, you can add a microwave frequency, and then levels plot will actually show you where the resonances are. So you just define a microwave frequency here in gigahertz, and then you add it at the end as a new input. And if you run that, you should see the transitions. You can see 1, 2, 3 transitions. The higher two are the single quantum transitions, and the one further down is the double quantum transition. This way you can explore for a given spin Hamiltonian and a given magnetic field and orientation where the resonances are and between which levels they are. So that's energy level diagram. The last thing I would like to mention briefly are line shapes. So the two major types of line shapes in EPR are Gaussian lines and Lorentzian lines, and they also can be combined into a line shape called a Vogtian line shape. And EasySpin supports that. So let's start out clearing everything. Let's define a linear vector of magnetic field values. So lin space goes from 300 to 400 MilliTesla, and let's take 1001 points. Lin space, for those who are not familiar with it, it's a very useful Matlab function. Let's come up with a center field, let's say 340 MilliTesla. This is all MilliTesla, and some full width of half max of 10 MilliTesla. Now we can calculate a Gaussian line. I'm going to call that YG with a function called Gaussian. And what you need to feed it is the field axis, then the center field, so where that peak is actually centered, then its full width half max, and that's it. And you can do the same thing for a Lorentzian line, just instead of Gaussian, you have to say Lorentzian. And we can plot this now by B, YG to plot the Gaussian, and then B, YL to plot the Lorentzian on top. If I run this, I get an error, not because my percentage here did not work out. And here we are. You see the Gaussian line is in blue and the Lorentzian line is in red. You can see the Lorentzian has much broader wings. It's also lower in intensity because the Gaussian and the Lorentzian functions are both normalized, meaning the integrals over these functions are equal. The Lorentzian is a little truncated. You can see it extends beyond the field range, so the integral will not quite be 1. So let's say if we define the field increment dB as being just the difference between the first two B elements, and we sum over the entire line shape, YG, and multiply it by dB, that is kind of doing like the integral, right? And we can do the same for YL, and just now check when running this code here, F9. See, the Gaussian cleanly integrates to 1 because by the time we hit the edges of the field range, it's really completely decayed. Whereas the Lorentzian only integrates to 0.93, and the reason is that it's truncated. If you had a larger field range, that integral would approximate 1. You can also get a combined a Vogtian line shape. And there's a function for that, an EasySpin function for that. Let's say you have a full width half max Gaussian of 10 MilliTesla, and a full width of half max for the Lorentzian component of 3 MilliTesla. Then you can get the combined Gaussian Lorentzian line shape as Vogtian, and again the B-axis, the center field. And now for the widths, you have to supply both of them. Full width half max for the Gauss and full width half max for Lorentzian. Okay, and then we can just plot this, B and YGL. And you can see we have now an overlap. We have something that drops down very steeply, but has then some tailing like Lorentzian. And the steep drop is due to the Gaussian. So this Vogtin line shape is what's being used in EasySpin if you supply both a Gaussian and a Lorentzian broadening. And it corresponds to like a Gaussian convolution of a Lorentzian line shape or a Lorentzian convolution of a Gaussian line shape, depending on how you like to look at it. So this is a brief overview of some other tools in EasySpin. So we talked about physical constants, we talked about spin operators, spin Hamiltonian matrices and how to calculate their eigenvalues and eigenvectors, energy level diagrams with the function levels plot, and finally, at the end, we talked about the different line shape functions that EasySpin support. We're at the end of this first session of today. Now there's a roughly 9-minute break. And after that, we reconvene for the second session, which will be about simulating ENDOR spectra. See you there.